protection. By the resilience of fat forms a protective cushion for certain organs against excessive pressure and mechanical injuries by jolts. The fat in the soles of the feet may be considered as acting like rubber heel. The fat around the eyeballs prevents this delicate organ from being injured by the jars which the body frequently receives. So it also protects the organ. Then contour. Actually, we already know. Properly distributed fat gives a pleasing contour to the body. Improperly, storing of the fat in adipose tissues sometimes becomes excessive, and the body weight and bulk increases beyond what may be regarded as normal. It is then not only unsightly, but also is constant threat to the health. Well, we don't have to worry about too much about. So these are the things you must understand about calories. I'll just give you calories, how to, in case if you want to diet, this is the final thing to understand. When overweight individual is to reach and maintain average or ideal weight, not only must he reduce the daily food intake, but also establishes new eating habits. Therefore, the long-term reducing diet regimen rather than the short-term strenuous diet is recommended. Just few days fasting for 10 pounds lose, that is not going to work out the system. Not too much exercise. You think, oh, if I work too much, exercise too much, then I'm going to burn so much of my. That also doesn't work. Why? Because after exercising, you've reduced your carbohydrate, so you want to go and eat more. So that what you spend already, you replace it by eating. So adjustment with the diet, exercise, together only you can control. By either by diet alone you cannot control, or by exercise alone you cannot have moderation. Nor a complete few days fasting and lost, like Mary Russell. She lost about 25 pounds or something in the last course. But she said she's going for this advanced course, so she's went to see her tenants to get some money or something. She's going to come back very soon. But now she is putting on a discipline what she had, she couldn't do that. When she comes out, she'll be having another 25 pounds. So have moderation should be there. So here it is a technique, how to synchronize both. The time required for an overweight individual to reduce to average or ideal weight depends on the rate of loss, the amount of excess poundage. It has been shown experimentally the average person can adjust quite readily to a diet regime. It provides for a weight loss of 2 pounds per week. Since 3,500 calories are equivalent to 1 pound of body weight, a 2 pound per week weight loss can be attained by omitting 1,000 calories per day from the diet necessary to maintain present status. So if you are 160 pounds, if you can reduce just 1,000 calories, not just fasting completely for several days and then eat afterwards, that's not. 3,500 calories is almost 2 pounds of the body weight. And if you take 1,000 calories reduce in your daily diet, then what happens? You are able to reduce in 1 week how many calories? 7,000. That means 2 pounds. So in 3 days or 3.5 days you can reduce 1 pound. So that's all. If you can keep this balance, there's no problem. But again, some people may not get the result. So again, exceptions are there to all the rules. Like Swami Dattatrayanaji. If she puts on this regime, it may not work at all. So she must reduce the food much less and increase the expenditure. So she must run 10 miles a day Or every day she must go to send a gut to banking by running, like the postman old postman do along those days. You see, if you can do that, you'll be very wonderful. Okay, better do that fast. Okay, you finish your advanced course. Reduce during the whole winter. You got enough fat to survive. So you don't have to eat at all for whole eat, and we can save lots of money too. No, I mean it. You must start a regimen diet. At least start with 1,000 calories a day. Reduce it and see what happens. You see, and keep your increase the sun exercise and just a walk every day. Take a nice long walk to the lake, and check up our properties are all good, our farmer property, and just for an inspection too. You see, keep it a regimen, okay? Because now you got ample time of the seasons are over, and you will be here living in this cold climate, and you got no problem for the heat, and no problem for the food because you can survive everything you already stored up for the next 6 months. You got enough everything, okay? But reduce it. I want to see that you put a strict program, okay? And practice also shoulder stand to control the thyroid metabolism more. So calories are equivalent to 1 pound of body weight. A 2 pound per week weight loss can be attained by omitting 1,000 calories per day from the diet necessary to maintain present status. Although physically active persons appear to have less tendency to become overweight, it is generally futile to attempt to reduce body weight by exercise because the metabolic cost of the common exercise are small. It has also been shown that exercise is powerful stimulant to the appetite, and then after a bout of work, the individual tends to eat more than necessary to pay the metabolic cost of the exercise. You have to pay for it. So you think that you can burn by more calories when merely exercise alone is not going to, because you are going to eat more. Then promiscuous use of drugs should not be practiced as a means of reducing body weight, since this approach to the weight reduction problem may prove dangerous to health. Because there are so many ways now. They said complete high protein diet, they will give you liquid protein diet, but there it is. It's all very dangerous, injurious to the liver, to your system. And some drugs they give, it's only to reduce the, not actual body weight, it reduces the water. So about 3 pounds by taking this, you are not losing anything, only the water is been taken off from your body. And that's also very dangerous. Dehydration will take place too. So many of these so-called, and also some, they give high hormones type of things to activate your pendulum, burning up fuel. These are all very dangerous things. So don't follow all those fads to reduce. Practice yogic exercises, which is not neither too fast, you are not burning too much, and sun exercise, very moderate exercise. Increase from 10 to 12 to 14 extra additional sun exercise, and then reduce the food little bit of everything. With protein you cannot store, so don't take too much protein at all, so the body doesn't have to work too hard, and reduce the intake of fat, and also moderate the carbohydrate. Make a balanced diet. These three things, if you put together, the vitamins and minerals, everything is there in your vegetables. You are vegetarian, you don't have to worry about extra additional vitamins, supplements. If you want, you can take additional vitamin supplements, but beyond that, a vegetarian do not have to worry about any food problem. The meat eaters has to worry, because meat contains no vitamins, no minerals, maybe little, but what is there is all mostly fat, cholesterol, uric acid, which are, and high nitrogenous waste. These are the conditions which you have to. That's why vegetarian diet is the best diet. If you don't believe it, practice it. And then one day you will see that you will live as long as you breathe.
One problem with the vegetarian diet, people changing from a meat diet to a vegetarian diet, or changing their diet very quickly, they have different deficiencies.
There is no different deficiency, it's all just imaginations. What is happening is they just change it from vegetable, meat to vegetable, but they are not taking the vegetables lintels and other things necessary for them. They are maybe just changing in a decade. You already heard about all these things. What are the things necessary? Where you can get the protein, lintels and protein, soya beans and milk and cheese and all contains protein. Even potato contains protein. You know? Do you know that? Even potato contains protein. Even rice, potatoes, wheat, cabbage. It contains protein is everywhere. In fact, there is no place there is no protein. Where do you get the big elephant gets the protein? Hay. They don't even get the hay. They just Vietnam jungle and the Thailand jungles and Indian jungles. They just thrive. Just eat only bamboo shoots and food they can find it. They eat anything, they can find it. And where do the cows and cattle in the natural state, wild horses, where do they get their protein? From the grass. So the original source of energy is, of course, they eat lots of grass, etc. But the body weight also is quite heavy. So, but we cannot. Our liver can be broken. Now you can see everything, every foodstuff affects the liver.
A system that's habituated to having lots of protein needs much more protein.
No. That's again. You look at that. All these things you just now heard. Your body cannot store even a small amount more than what is necessary. You heard that.
Right.
And then you are talking about the body is accustomed to more protein. How can the body can accustom? Body is only accustomed to eliminate the extra protein.
But if it metabolizes the protein into carbohydrate, then it takes lots of energy.
You heard the whole thing. The metabolic of the carbohydrate, the protein into carbohydrate is very limited and very small. But for that, the liver has to work very hard, nitrogenous waste. So all the energy you got it, you are wasting through the converting the nitrogen into nitrogenous waste, urea. You heard all those things, and yet you are arguing the wrong thing. Think about that. Om Shanti. And then
what cells are irritable?
Are irritable, but even relatively early in the course of evolution, some became more irritable than others.
you understand? You can hear it?
Yes.
Thank you.
Among these cells, certain ones called receptors became especially sensitive to stimuli.
Okay. Let us stop here. We had the two words you'll be learning now. Receptors. Write that word. Receptors. R-E-C-E-P-T-O-R-S. Receptors. Example is skin. The sensation coming from the skin. Skin receptor. Receptor.
Okay. Others were especially adapted to conducting impulses and formed a network of nerve cells or neurons, the first nervous system. This crude system enabled the lowly organisms in which it arose to achieve a grade of integration somewhat above that of the one-celled amoeba.
Can you understand it?
Can you say that again? I can hear the words, but they didn't necessarily register.
Others were especially adapted to conducting impulses and formed a network of nerve cells or neurons, the first nervous system.
The first nervous system, how it is being created.
This crude system...
Wait. Don't just run. First nervous system. It has got one receptor and then what? Neurons. To carry the impulse. So, a nervous system is born, a simple nervous system. Okay, read it.
This crude system enabled the lowly organisms in which it arose to achieve a grade of integration somewhat above that of the one-celled amoeba.
One-celled amoeba, you know one-celled amoeba? It has got it's nervous, but when a stimuli is applied, it will, without having any nerves. So from that it came this first nervous system developed. Yes.
Right. When worms evolved from the lower forms of animal life, ganglia or clusters of nerve cell bodies made their first appearance.
Okay, right, ganglia. Second word. Ganglia means a cluster of nerve cells.
These acted as primitive centres of coordination of activities. Each body segment contained one or two ganglia. The neurons of the ganglia served as intermediaries between the afferent neurons.
Well, just to stop there. There are one side there is receptors, and other side is connected to a muscle or a gland. The purpose, suppose I touched a hot stove, it's very hot. So what happened? Receptor gave an impulse through the neuron. This is called afferent impulse. Afferent. A-F-F-R-E-N-T. Afferent.
What does that mean?
Afferent. It carries the impulse, sensory impulse, sensory to the brain or to the spinal cord. That was coming out soon. It is going inward. The sensation going is called sensory also. Afferent or sensory. And that impulse will come eventually to the spinal cord or the brain, but we'll come to that soon. And it must be immediately brought to a muscle, which is the muscle involved to take my hand off. And so that impulse will reach the spinal cord and shunted back to a flexor muscle or extensor muscle according to the nature of the motion. So what I have to do now, flexor muscles are involved. That's called efferent. E-F-F-E-R-E-N-T. Efferent means towards the muscle or gland.
Between afferent neurons, which conducted nerve impulses into the ganglia from receptors, and efferent neurons, which relayed impulses to effectors, muscles or glands.
So receptors, and the next word is effectors. Effect. Receptors, effectors. Receptor and effector. E, effect. E-F-F-E-C. Effect. Effector. So receptor and receptors send afferent impulses, and this is brought through the neurons, the ganglia, and then these impulses are transmitted to the effectors through another set of nerves or neurons. And those set of neurons which carries the current, when it's brought and then it goes into the effectors, that is called efferent current or motor impulses. Another word. So sensory and the motor are afferent and efferent. So these two were the first thing we have to learn to understand the nervous system.
So an afferent.
You don't have to worry about too much all these things. Just write all. Make this very clear. That's all more. That's most important thing. Yeah, that's the grammar of this. Make it very. Don't let just come on, just go on. Fast. very important. That side. Next.
In this way, simple reflex circuits were established.
Simple reflex circuit. A circuit like in a battery, in a bulb. A battery is connected to a small bulb. Two wires going, and then one wire, the same wires after connecting coming back and joining the same, almost like same circuit. So a simple circuit, receptors and what are the two names? Receptor and effector. And receptor sends an impulse through a, and that's like a wire, electricity, and that impulse is brought through spinal cord, which we'll discuss now soon, to the gray matter in the spinal cord, and then brought back into another neuron, and carries this impulse in the form of efferent current to the effectors. A simple circuit has been formed. Yes.
In time, connections between ganglia developed, and chains of ganglia came into being. Such interconnected ganglia became the first real message center for nerve impulses, or in other words, a central nervous system was developing. At this stage, the central nervous system reminds one most of the spinal cord of higher animals.
There was no brain. There was only, in the early stage of central nervous system, is without any brain. The spinal cord did all the work.
Even in man, the latter retains its segmental pattern.
What is the latter? The latter. What is the latter? Still, the spinal cord plays a great, important part in our daily life. The brain is not doing all the work. You thought brain is doing all the work, is it not? Spinal cord is doing lots and lots of work. The same circuit, what happened before the brain developed, the spinal cord, and the same function what did spinal cord did, still function in human being. The simple same circuit is going on.
At the worm stage of evolution, the head was beginning to assume dominance over the rest of the body. Since the head end was the first to encounter stimuli as the animal moved, the more important sense organ, eyes, ears, etc., developed in this region.
So not only brain is the center, the head is the center for the further development of this central nervous system, but also seat for all the sensory organs, sight, seeing, senses like eyes, ears, and so on.
Coupled with this development, the ganglia of the head segments began to fuse with one another. The larger nerve cell centers resulting were the forerunners of the brain. The oldest, in an evolutionary sense,
you give all the prominence to this, and no prominence at all that is. Just make it deeper and strong and fast within so much time.
The oldest, in an
Start again beside and here.
Okay. Coupled with this development, the ganglia of the head segments began to fuse with one another. The larger nerve cell centers resulting were the forerunners of the brain. The oldest, in an evolutionary sense, parts of the brain in higher animals retain traces of primitive segmentation, although to a lesser degree than the spinal cord. In the invertebrates, the central nervous system, ganglionic chain, is a solid cord of tissue, the head ganglia being dominant. In the vertebrates, the central nervous system is a hollow tube.
That will be learning that the spinal cord, that's a hollow center.
The walls of this tube ultimately grow into the organs we know as brain and spinal cord. From either side of the brain and spinal cord, the cranial and spinal nerves extend to all parts of the body. These nerves constitute the peripheral nervous system.
So there are two words we are going to learn now. One is central nervous system and Central nervous system consists of brain and spinal cord. And other than these two is called peripheral. What do you mean peripheral means? Outside. So the two words we are going to learn, central nervous system and peripheral.
Every neuron consists of a cell body and
Wait. The physiology of nerve.
The physiology of nerve.
Why don't you read that?
Right.
It's very big there.
Very big. Huge.
You don't want to
Missed it altogether. The physiology of nerve.
Don't worry about that. Just make all the space. You just finish it. Just give me the time. Because if you are going to write that good name, never finish anything. Come on, fast. I do all those things. Just make this picture and go get out.
Well, that's all it is.
No, okay. It's not very solid. We will look properly. No, not happy. First, what do you call that? Sensory surface. Huh? What you call, what you done just now? Receptor. That is the receptor. Skin is a receptor. From there, or before that, let us see nerve fibers, connective tissue. Here is a cell, nerve fiber inside, and the connective tissues. And then, before we go further, just watch here now how a neuron is created, so that it is less difficult to understand. A typical neuron, the whole thing. In the neuron, there is central nucleus like any other cell, and then cell body around, and then there are various branches going out from the cell body. What do you call that? That's called dendrites. Which you didn't write that, huh? Look at this. You didn't write it. Right. So these are the branches. So cell body, dendrites, and next is one long thing. This is called axon. A-X-O-N, axon. These are the main neuron structure. Cell, repeat again. Cell body around, and then the branch is called dendrites, and then axon. And the rest of the things are like insulation. The first insulation for the axon is myelins, M-Y-E-L-I-N. That's the first insulation, which you got this afternoon with the cholesterol we were talking about, myelin. Next is N-E-U-R-I-L-E-M-M-A, neurolemma. N-E-U-R-I-L-E-M-M-A. And here is naked axon ending in N, like tufts, ending in various branches like tufts. These are the a neuron structure. If you can remember this, rest of the things will be very easy. Can you remember this? Nucleus, very simple, and the cell body naturally surrounding the nucleus, and then it goes into two sections. One became dendrites, which is several, you can see, but there is only one long arm. It is called axon. And that axon is got insulation. The two insulations are there. In some place, of course, there will be only one insulation. Will come to the later on. But just learn this. Okay. Once you got that neuron, so here a afferent fiber. That means a neuron which brings. Okay, I will have to make it bigger diagram. It's too small. Okay, let us go further. As long as this was there, I'll come to that later. Okay, read it now. Continue.
Okay. Every neuron consists of a cell body and various extensions or processes.
Every neuron has got a cell and cell body, and then what else?
Dendrites and axons.
Start again. That's
Okay. Every neuron consists of a cell body and various extensions or processes, dendrites and axons.
dendrites and axons.
Most neurons have many dendrites.
Many dendrites it is got, see, but only one axon.
Okay. Most neurons have many dendrites, are multipolar, all of which conduct impulses to the cell body. Every neuron has only one axon, which conveys impulses away from the cell body. In general, axons are much longer than dendrites.
That you can see here. Dendrites are small, axons are long.
Some axons in man, for example, may be 3 or 4 feet in length. A number of axons and dendrites bound together by connective tissue constitute a nerve.
So what is a nerve? What is a nerve?
Several axons bound together.
Not several axons. Okay, next.
Can you
No.
do that again? I
Read it out.
Okay. How much?
Read that.
How long can axons be?
3 to 4
That's the longest one. Generally it is not. Okay.
A number of axons and dendrites bound together by connective tissue constitute a nerve. Nerve should not be confused with nerve fiber,
Fiber.
the latter being another name for an axon or a dendrite.
So there is difference between nerve and the nerve fiber. This is a nerve fiber. This is a nerve fiber, this all. But a nerve is when this all connected by a connective tissues to form one nerve. Next.
The properties and function of nerve fibers. Nerve fibers are more irritable than muscle and therefore respond to stimuli of weaker intensity. Nerve fibers are also more conductive than muscle. Thus, an excitatory state set up in a nerve fiber is transmitted more rapidly than in muscle. The conduction of an excitatory state, the nerve impulse, is the sole function of a nerve fiber.
Okay, make that note. Read that sentence again.
Nerve fibers are more irritable than
No,
muscle.
not just the last sentence.
The last sentence. Thus, an excitatory state set up in a nerve fiber is transmitted more rapidly than in muscle. The conduction of an excitatory state, the nerve impulse, is the sole function of a nerve fiber.
Read that. That's the sentence you have to read it so they can write it. Read it please again. That same sentence what you read now.
The conduction of an excitatory state, brackets the nerve impulse, is the sole function of a nerve fiber.
Correct.
Actually, the conduction process is more than a passive affair. The nerve fiber plays an active role in transmitting the nervous impulse along its length once the impulse has been set up in it.
That means it takes an active process. This process of transmission of that impulse is an active state. It's not a passive one. The fibers takes the responsibility of transmitting this impulse to the next neuron, because neurons are not connected, joined. That's a junction, we'll come to that. At that time, it's passed on from one junction to another.
We shall see a possible explanation of how this is accomplished a little later. Meanwhile, a crude analogy may help to clarify the action of the nerve fibre. Imagine a row of 10 pins, one pin directly behind the other. Let these correspond to successive points on a nerve fibre. A ball is bowled at the first pin, and its impact, the stimulus, knocks over the pin. The first pin, in falling, causes a second to fall. The second hits the third, and so on. The continuous wave of motion created by the pins falling in series would correspond to the nerve impulses. Actually, much like a wave of electricity. And
So, easiest way to understand is motion of the electrons through the wires. That's called electricity. Similar, the nerves, something like wires, but still quite different because there are each is not connected directly. That impulse has to jump from one junction to another.
Each pin, in turn, is necessary for the propagation of the wave. The stimulation of nerve. A stimulus adequate to excite a nerve must fulfill the conditions already quoted for muscle. It must be of minimal strength, last long enough, and reach minimal intensity quickly enough.
So that is how a stimulation of the nerves are brought into. First, read again.
It must be of minimal. It must be of minimal strength, last long enough.
Minimal strength. That means if the strength is below that minimal strength, the the nerve will not send any impulse. The impulse may be coming, but the effectors won't have any effect. Second,
Last long enough.
that means it must have certain duration.
And reach minimal intensity quickly enough.
Next.
Unless it has these characters, the nerve will not respond to it. In the body, nervous impulses are generally set up at one end of a nerve fibre.
When I did mildly, it did not great.
Concentration, see. In the body, nervous impulses are generally set up at one end of a nerve fibre. The axon of a neuron, for instance, receives a nervous impulse at its point of exit from the cell body.
Cell body, that is the exit. So it gets impulse, this axon gets from here.
The impulse then travels in one direction only.
It is one-way traffic.
But if a nerve is exposed or a long segment of one removed from an experimental animal, it can be stimulated effectively at any point. The nervous impulse so produced will travel in both directions along the nerve fibers.
But that is only if it's severed and then certain things are created. But in generally, it can only go through one direction.
Nerve is like muscle in that it will respond to electrical, chemical, thermal and mechanical stimuli.
And like muscle cells, these are all will bring certain type of stimulation. But the highest and most powerful stimulation you get from the electrical impulses.
In the great majority of cases, electrical stimuli are of the greatest significance. Sometimes other kinds of stimuli set up nerve impulses. For instance, the peculiar sensation you receive when you hit your funny bone is due to stimulation of a nerve in the arm by pressure.
Which is the funny bone.
Normal nerve impulses in the body are probably set up by environmental changes of electrical nature. For experimental purposes, artificial electrical stimuli are, Then the closest approximations of natural stimuli.
You can connect a frog muscle to a small wires and electrodes to a battery and give a small electrical current, the same like nerves. It will pass through and then do the same action as the nerves do. A simple example of, because this will relate you later on to understand prana more.
Electrical stimuli also do less damage to tissue and are more easily and accurately controlled and measured. In order to study a nerve, it is essential to record its activity. This is more difficult than for muscle because nothing can be seen to move in an active nerve.
Because muscles, when it contracts and relaxes, the nerve there is no motion, so you can't see it.
Sometimes we can get information about nerve by recording the muscular contractions resulting from nervous stimulation.
That's the only time you know that. When muscle contracts, you know that the nerve impulse is coming through. That only, there you find out that action is taking place.
A much better method has been devised, however, which involves the use of delicate and complicated electrical apparatus. Such apparatus amplifies the extremely small fluctuations of electricity that occur in nerves so that they can be recorded and measured. Through modifications of such apparatus, it is actually possible to visualize the nerve impulse and then photograph it. The nerve impulse. The analogy between a nerve fibre and a series of tenpins is, as we saw, a very crude one. Structurally, of course, there is no resemblance at all, and the kinds of action going on in the two cases are very dissimilar. The analogy also breaks down in another very important aspect. In order to repeat the 10-pin phenomenon, it is necessary to set them up again. They obviously have no recovery power of their own.
Yes, I think now it is modern, what do you call, bowling area. When you knock down it automatically, but it's not done by hand. Same, the machine does that. So, well, that was the analogy, but generally, originally, just someone has to go and put it back, but here the recovery takes place naturally.
The nerve fibre, however, after the passage of a nerve impulse, brings about its own recovery. A short time after it has conducted one impulse, it is once again ready to conduct another. The membrane theory. The most satisfactory explanation of how a nerve fibre conducts a nerve impulse is the membrane theory. According to the theory, the nerve fibre is surrounded by semi-permeable cell membrane, a membrane which allows only certain substances to pass through it.
Well, we'll just skip that question.
Yes, shall we?
Let me see what portion first.
Membrane theory.
Receptors now we are going to discuss about.
Control of tissue activity. Neural control. Receptors. The power of adjustment to its environment is the paramount characteristic of a living being. To enable a more highly organized form of life to adjust itself effectively to environmental changes, certain organs, by their construction, are eminently fitted for detecting changes occurring externally to those organs. Receptors are highly specialized end organs which raise the threshold for some types of stimuli and lower it for others.
Can you read this? This one? Very difficult. Can you? Okay, what I'll do that I'll make this whole thing to a very big one. Because this is very important here because this spinal cord comes there. It's brought. There are two matters there. What are the two matters? Grey matter and white matter. There are two horns. If you don't understand what is grey matter is, the center, it looks like edge. If you cross section, if you cut the spinal cord like that, say this is spinal cord, if you cut it straight, it will look like this H, something like H. Something like H. So there are 4 horns you can see. 2 upper horn and 2. The one which is behind is called dorsal horn. One is in the front is called ventral horn of the which matter? Grey matter. That's very important to remember. That's the grey matter. And the rest is all white matter. First, we are not discussing anything with the white matter. We are only interested to this, how the first impulse coming in the first, before the brain start developing or anything like that, came spinal cord itself. Most of our function even now is performing. That's what we are talking about. So the receptors, you get a nerve impulse and then brought to the gray matter in the spinal cord. It ends there. Now there is a junction called synapse. So there another neuron is taking the impulse and then relays to third neuron. That is called, this is called afferent. This is the, so from here onward it is different, afferent, and goes to a muscle fiber. That's the muscle. This impulse brought to the muscle fibers and the muscles will contract. So the direction of the, so it came from here impulse, but in the spinal cord it is transferred to another interneuron. We'll come to that, interneuron. So the 3 nerves are there, 2 neurons are involved, nerves are involved. Incoming signal in the gray matter it is being shunted to another interneuron, and then outward it is taken by third neuron, that's called the motor nerve or efferent current, and the muscles get it. This called, what is called this one? What do you call this one? Come on. This is called receptor and this is called effector. So here the impulse coming and that is come to the muscle. But before it comes, it came through the gray matter of the spinal cord. So 3 things. Make this diagram, please. This is cross section of your spinal cord when it's cut like that vertically, and they are looking from the top. There is inside horns, and there is a small canal, central canal. Leave that open and put a receptors as a skin, and then put a second neuron and then another one, and then we'll understand the whole process of the full circuit. Okay, read it now.
Some receptors, such as the eyes and ears, are excited by environmental changes. These are known as exteroceptors. The interoceptors are stimulated by changes occurring in the body itself. Effectors. Specialized organs for adjusting the body or a part of the body to the changes reported by the receptors have been evolved, namely muscles and glands.
So, receptors, mostly we can call it muscles and glands. So, sorry, no, it's not right. You read that. No.
Effectors.
Effectors.
Specialized organs for adjusting the body or a part of the body to the changes reported by the receptors have been evolved.
So, effectors, read again, you'll say, effectors been evolved
Namely,
to take the reaction coming from the receptors.
namely muscles and glands.
Read again that sentence whole.
Specialized organs for adjusting the body or a part of the body to the changes reported by the receptors have been evolved.
What is the Suppose this is skin. If it's touch a hot stove, then the effectors will be brought into action to escape from that particular sensation or experience.
Go on.
Yeah.
Physiological connectors. To serve as a line of communication between the receptors and the effectors, which frequently are situated at widely separated parts of the body, is the primary function of the nervous system. In the opening chapter, we briefly mentioned the necessity of a coordinating mechanism by which the activities of the many organs are controlled so as to result in integrative action. This mechanism consists of two distinct parts, the neural or nervous system and the humoral or chemical.
The two, one is the changes are occurring through the nervous system, the neuron, and another is chemical.
The neuron. The nervous system may be divided into the central and peripheral systems.
That you already know now. Central nervous system is brain and spinal cord.
The former includes the brain and spinal cord, and the latter, all the various nerves which spring from the central nervous system and pass throughout the whole body. This system is made up of anatomical units known as nerve cells or neurons, which is Greek for tree. Nerve cells or neurons differ greatly from each other in size and outward appearance. In general, the cell body of a neuron gives rise to one or more much-branched processes, known as dendrites or dendrons,
Which you already know by this time.
and to an axon. Usually the axon is of greater length than the dendron, and is generally spoken of as a nerve fibre. In the central nervous system, the axon may give rise to one or more side branches or collaterals, and it may terminate in an end tuft.
Okay, we first
It's,
already by because you can say that.
the end tufts make physiological connections either with the cell body or with the dendrons of another neuron.
So that is how the this is called dendrites, nucleus and cell body, and then axon, and here axon ends in and tuft, and then it joins with the dendrons of the next one, or to the muscle fibers, to a muscle like that, or to the neurons. This way chain comes up. Next.
Grey and white matter. In the CNS, which is the central nervous system,
So remember the word CNS. CNS means central nervous system.
the millions of neurons are arranged in such a manner that the cell bodies are grouped together in masses. These are greyish in appearance. In the cylindrical-shaped spinal cord, this grey mass forms a central column throughout the length of the cord.
So this is the spinal cord cut, and this central portion, the grey matter,
This constitutes its central grey matter, CGM.
CGM, central grey matter.
In-
Also you'll hear CWM, central white matter, CGM.
In cross-section, it has somewhat the shape of a capital letter H.
See, it looks like this, grey matter looks like H. If you don't know how the H is written in English, you know how to do? This is the way H is written. And you see, it's almost like that. So if you can remember grey matter and H, easily you won't forget it.
Got a soft H or hard H?
Huh. Yeah, that's good. That's a picture I think in our
But it's not as
That,
complete.
wait, just look into that also, but extra you can get from here too. Okay.
It's not as complete as what you have up there.
Okay, next.
The nerve fibers springing from these and other cell bodies are arranged in bundles around the CGM. And
CGM. So nerve bundles, what is gray matter is, what is gray matter? Is made up of what? Of bundles of, read again. Come on, read it.
yes, millions of neurons are arranged in
Slowly, millions of
neurons are arranged in such a manner
these type of millions of neurons are arranged in such a way
that the cell bodies are grouped together in masses. These are greyish in appearance.
so that millions of these neurons bundled together, it appears to be like grey.
The nerve fibers springing from these and other cell bodies are arranged in bundles around the CGM and constitute the white matter of the cord.
Okay, that's the white matter of the spinal cord. The grey matter, no white matter. Read once more, white matter.
Yeah.
CGM means central grey matter. Now the CWM, repeat the
I think I'll
CWM.
have to read this whole thing
Okay,
in one
read.
hit.
Okay. First, then I explain to you. Okay, read.
In the CNS, the millions of neurons are arranged in such a manner that the cell bodies are grouped together in masses. These are greyish in appearance. In the cylindrical shaped spinal cord, this grey mass forms a central column throughout the length of the cord.
Throughout
This
all the way.
constitutes its central grey matter, CGM. In cross-section it has somewhat the shape of a capital letter H. The nerve fibres springing from these and other cell bodies are arranged in bundles around the CGM and constitute the white matter of the cord.
Read the sentence again.
The nerve fibres springing from these and other cell bodies are arranged in bundles around the CGM and constitute the
Around
white
the
matter.
grey matter, there is other neurons are there, and they are also arranged in bundles, and that look a different kind of color, just to differentiate from the function of the grey matter and the white matter, which will come later on, and each one has got different functions there. This also will help you to understand when you understand nadis, because there are ida, pingala, etc., and that from to the white matter, the impulses will go up and down to the brain and down. So this will be coming soon. So only just understand the white matter exists outside the grey matter. That's all you have to understand now. As we go further, we'll understand further.
The spinal cord may be divided into a number of segments. This is figure 26. In it are shown two neurons, greatly enlarged.
These are, in fact, that must be three.
Yeah, that's this one here.
So that's always good, but there actually must be three. Okay, let's go.
The neuron, having its cell body in the CGM, sends its nerve fibre out of the cord to make a connection with a skeletal muscle.
See, from here, the grey matter, a nerve fiber, a nerve is going out to innervate what? An effector muscle. So one section you can see.
The other neuron has its cell body located outside the cord.
So this cell body is located inside, and the other one is located outside.
One of its processes enters the cord and ends somewhere in the CGM.
So CGM, central grey matter. It came here and entered somewhere here. Because between this and this, there will be a third neuron is there, like interneuron. But that will come later on. So forget about interneuron now. So one is the effector is bringing up, and from the grey matter goes the receptor bringing in, and from the grey matter goes to effector.
The other process extends to and ends in a sensory surface or sense organ.
This is called sensory surface.
The central terminal branches of these two neurons make synaptic contact with each other in the central grey matter.
There is a contact, this is called a neuron when ends, and then another neuron, this contact is called synapse. This one neuron and the other neuron starts like that. In between there is a small minute gap. It is not directly connected this and that, no, not directly. This place, the impulse is transferred into this neuron, and that has been transferred there. But in this, a simple circuit is without this. Let us assume later on it comes to interneuron. That's called. Suppose now this impulse came and went into the receptor to the effector. Then later on I will show you the interneuron. Okay.
Dorsal and ventral roots.
Now that's very important to remember. Dorsal and ventral. The dorsal is posterior and ventral is anterior. Ventral is anterior, dorsal is posterior. So here, this is ventral, bottom one. So the bottom two is ventral horns, they call it horns, like a horn of them. And the top two is the dorsal horn. Now, always afferent current or impulse coming through the which horn? Dorsal horn. And the efferent goes through ventral horn. So the dorsal entrance, always the impulse coming to the dorsal and going out through the ventral. Read now.
The fibers of some of the cell bodies located in the CGM of a given segment of the cord are grouped to form what is called a ventral root.
Ventral root. These are the two ventral roots.
The processes of the cell bodies located outside but very close to the cord are grouped to constitute the dorsal roots. 31 pages. The fibers of the dorsal and those of the ventral root of a given segment of the cord unite to form one bundle of nerve fibers called a spinal nerve. The cell bodies of the fibers constituting a dorsal root are grouped in a small mass lying in the root. Such a collection of cell bodies outside the central nervous system is called a ganglion.
Okay, now a ganglion is coming up. A neuron is coming, and before it came into the gray matter, there is this is called a spinal ganglion. Again, I'll make it clearly. This comes up, spinal ganglion. And then it comes to the dorsal side of the spinal cord. So that is called spinal ganglion. You can write it if you want. Spinal ganglion. In the other side you don't see it. The ganglion is only on the incoming, not outgoing. You ready?
Right.
Okay.
Afferent and efferent nerve fibers.
Okay, spell the word.
A-F-F-E-R-E-N-T and E-F-F-E-R-E-N-T. Afferent and efferent nerve fibers. The impulse generated by the stimulation of a receptor or sensory surface is transferred to a nerve fiber, which conducts it to the spinal cord.
See, this is Afferent. Next.
Since this fibre carries the impulse to the central nervous system, it is known as an afferent nerve fibre. Brackets, add forward, ferro, to carry.
Afferent comes from that add, forward, to carry, the impulse, to carry into the central nervous system. Which is central nervous systems? Brain and the spinal cord.
The afferent fibre enters the cord by a dorsal route,
Dorsal root, the top, behind root.
and the impulse it carries is transferred to the central grey matter, to the neuron which conducts it out of the cord to an effector. This last named fibre is, therefore, an efferent fibre.
This is called efferent fiber. This is afferent fiber, efferent fiber.
X out.
X out, afferent means X out, exit.
It leaves the cord by a ventral route. Afferent fibres are sometimes called sensory nerve fibres. Efferent fibres are either motor, to muscles, or secretory, to glands.
So motor or secretory, to muscles and glands is called motor nerves. It's called efferent, and motor nerves are same. Afferent or sensory impulse are one and the same.
Spinal nerves are mixed nerves. Okay. Reflex actions.
Now next one is this, the important now coming. Now you know the simple structure of the neurons and the spinal cord. Now reflex action. How an impulse coming from the receptor and how it reaches the effector. And that simple technique, we are going very simple as possible I will make it. Okay, we got the simplest.
When a sense organ is stimulated and the impulse thereby generated finally reaches and stimulates the responding organ, the activity thus induced is called a reflex action. This action concerns the function of either a muscle or a gland. Nearly all the actions of our body are of this sort. To give only one illustration, a foreign body falls into the eye, and as a reflex, the tear glands secrete more abundantly. A reflex arc.
Now this is very important. Reflex arc. A-R-C. Write this word, reflex arc. What is a reflex arc?
The nerve chain between a sensory surface and a responding organ is known as the reflex arc.
So we will go back now to reflex arc. First we learn the receptors and the incoming signal. Now we are going to learn how the reflex arc means. Reflex arc contains three things. First, the incoming afferent nerve and nerve impulse through that, and then interneuron, another neuron in the gray matter, because the impulse is been transmitted into the gray matter to this interneuron, and then again the impulse has been transferred from there to efferent nerve to reach the effectors. Okay, now see, this is called full arc. This circuit, we call it this circuit is called full reflex arc. Okay, read it.
This arc is composed of three parts. 1. The afferent nerve fibre.
Okay, make a call this the one, three parts. First, afferent nerve fiber.
2nd, the efferent nerve fibre.
That is second.
And 3rd, the connection between these two fibres form in the grey matter of the central nervous system.
That is the third. No?
This connection we shall call a reflex centre.
So all these three together is called reflex. In the middle there is reflex center.
In a reflex centre, there are many points of close proximity between the processes of one neuron and those of another. The communicating mechanism between the opposed fibrils is known as a synapse.
This is called synapse. See that? Where the impulse transferring, it's not connected directly. but impulse coming. So also in the muscles also. This is not directly cutting anything. There's a muscle. This ends in synapse or synapse, whatever.
Well, it's not the same as the reflex center.
Coming up. This whole thing is coming to reflex. We'll explain now. Okay, read it now.
Okay. Synapse is made of
Synapse is only this junction connecting two neurons.
it is made of sine or sin together and actin to clasp.
Clasp. That's synapse. Clasp.
Reflex centers are always located in the grey matter of the spinal cord or of the brain.
So make this remember. Reflex centers are in the gray matter of the spinal cord or in the gray matter of the brain, in the central nervous system, both. Next.
In nearly all instances, a third neuron is intercalated between the afferent and efferent neuron.
A third neuron invariably. A
This,
third neuron is there in between afferent and efferent. Okay.
this is known as the internucleal neuron
Or
or interneuron.
interneuron is simple. Neuron and interneuron in between. So that is the interneuron. So in a reflex arc, three neurons are there. Incoming and outgoing and in between. Incoming is called afferent, outgoing is efferent, and in between is inter, which connects, brings this impulse to the. So the channel is only one way. Impulse cannot return back because the synapses will only allow them this way, not the back way. No reverse process.
The reflex action may take place on the same side of the body, homolateral,
Now this is only little bit more complicated, but we can explain very clearly. You got right side and left side of the body, or right side of the spinal cord and left side of the spinal cord. The spinal nerves coming from, this is the spinal cord, right ventral horn, right dorsal horn and right ventral horn. So also left dorsal horn and left ventral horn. So sometimes the impulse can come from here and go into the same side, but sometimes it also will go to the opposite side. So it can come from opposite side also. So this is what mentioning. Okay, read that now.
or the impulse may be carried by
First start again. See, when you start in the middle, the connection is.
the reflex action may take place on the same side of the body, homolateral,
That's called homolateral, the same side.
or the impulse may be carried by an interneuron to the motor neuron on the opposite side of the spinal cord,
Opposite side.
contralateral.
We'll make a diagram. This is very important for you to understand. Flexors, extensors, how it functions. Because some muscles are flexing and other muscles are also going to relax. Because all muscles start contracting, then you won't be able to. So some muscles contracting, so you'll see how the reflexes are functioning. That's why when you test the knee reflexes, we'll discuss that. So at least see, I'll remove this and make this. Okay.
So the opposite side is called
Contralateral. If any one member of the reflex arc is broken, the reflex action is impossible.
Okay. Just will you please now you can come here. That mic won't be able. The same thing, but come up here. But you have to do it a little faster. Simple, as we saw, but also complicated process takes place. When you already know flexors, extensors. In the flexor, when my upper arm flexing, how many muscles are involved? How many types of muscles? What type of muscles? One is biceps called flexors, and then what else? The triceps, extensors. So now, I am touching a hot stove. Only biceps get reaction. Reflex came like the way you saw from the afferent back into the effector through the spinal cord. I try to contract, but what the other muscle has to do? It has to relax. So another impulse must go in stretching, so that complicated reflexes are there, opposing muscles. One is called antagonistic muscles. One is the muscles active, and there are muscles also antagonistic. So the impulses are different. And sometimes these impulses also, antagonistic muscles now working, but it does in simultaneously, just like when you are walking. What are you doing in walking? You are, some muscles, your chain reaction taking place. You are contracting and relaxing, and from one you are going to another. So 3 or 4 types of reflexes are there. These are done the same procedure. Once you understand the basic thing which you just now learned, there are other things very easy to understand once you made the diagram. Okay, read it.
Voluntary actions. Besides reflex actions.
Okay, no, we are not finished with reflexes. Okay. So we come to voluntary actions little bit. Let me finish this diagram and then come put it back. You'll see this very important for you to understand also how the postures help you, asanas. Because in asanas always antagonistic muscles are also involved. Most of the all the postures you know how, forward bending, flexors, extensors, adductors, pronators, supinators, which you already know all these techniques. Once you know this, you'll be understanding how the muscle, the nervous system is being stimulated in different ways by creating various postures and keep the proper tone. Even though my bicep contracts and tricep stretches, to keep that, there is a tone in the muscles. This tone of the muscle is because the impulse coming to that muscle is in the same way reflex mechanism is going on. So when you keep in a contracted position for a long time, like in the asanas, in each posture you hold for a certain time, it creates certain type of nerve reactions in the both afferent and efferent. In another word, Ida and Pingala. We'll come to that. Slowly we'll come to the relationship between the Ida and Pingala and all these afferent or motor and sensory nerves. And then you'll understand what's the purpose of bandhas. We are not holding the bandhas to just stop the breath, but when you stop the breath, you are controlling these 2 impulses, afferent and efferent. Finish?
The numbers are
Okay.
corresponding to.
Okay, just read it out and then I'll explain step by step. Okay, go slowly. Okay, here are the same thing what you saw before. Here we are having 3 segments of the spinal cord. Before you saw only 1 segment. Now we have 3 segments to show you different types of circuits. The simple one which you explained saw from the same side. Now you will see also going the opposite side. Three segments are there to show different circuits. All right. Now just come to the first one. Let's go to the first one.
A sketch of 3 different levels of the spinal cord and some of the varieties of possible reflex are neurons 1, 2, and 3.
Neuron 1, 2, and 3. This is 1. Neuron 1, 2, and 3.
Comprise.
Is it not? Yes, neurons is not directly connected, but there is a junction. What do you call junction? Okay. So here is 1. This is afferent, the motor, so sensory. This is efferent, as also this particular thing is called. If it is a receptor, this is a effector. Now, here is also a, what do you call this? Effector. This is the, must be efferent nerve. This also a effector. And this is then what? This one is, this is the receptor. See, because it's beginning. So this is afferent receptors. This is a receptor, afferent, A. So the 3 your afferent nerve coming to an efferent, to an effect, through efferent nerve. In between there is one nerve. What is called that? We just got it. What's the interneuron? So 3 neurons are there. So one coming from the right side of the spinal cord came into the gray matter. From the gray matter there is, through interneuron it is transmitted, and then from there it transmitted into, so 3 neurons. This is called 1 neuron, then 2 neuron, the interneuron, 3rd neuron is called what? Efferent nerve. So afferent nerve, interneuron and efferent neuron. So 3. This is all 1, 2, 3. Okay, read now.
Okay. Neurons 1, 2 and 3 comprise a reflex arc,
Reflex arc, we already know what reflex arc is.
which is centered at one level of the spinal cord, but
This is centered, the receptor is centered on the right side of the body. Okay, next.
but which ends on the opposite side from which it began.
The effector is on the opposite side. When you saw the first time, what was it? It was on the same side. Okay.
A similar arc to this, but involving 2 levels of the cord, is illustrated by neurons 7, 8 and 9.
Okay, 7, 8 and 9.
Left side.
Okay, this is 7. That is the receptor. 7, 8, that's interneuron. This is the interneuron for this, and then 9 efferent neuron, and then effector, the muscle. So 7, 8 and 9. Okay, read it.
The arc containing neurons 4, 5...
No, you didn't read that. Come on, read that again. 7, 8 and 9.
Okay, a similar arc to this, but involving 2 levels of the cord, is illustrated by neurons 7, 8 and 9.
The same thing from this side. The impulse came to this side, and from here it went to that side.
Next.
Next.
The arc containing neurons 4, 5 and 6
4, this is the beginning of the receptor, 4. Then what?
5 and 6
Okay, 5, the interneuron, the 5. And then 6.
involves 2 levels of the cord, but ends on the same side on which it began.
So it began, the receptor began, and the effector also on the same side. In these 2 instances, opposite side.
Next.
Next.
Stimulation of the receptor leading to neuron 1
That is the neuron 1, that's the receptor here, stimulation of that.
may not be strong enough to cause a discharge of neuron 3.
Suppose here when the energy is coming, because energy I am using now, because prana you will understand the better later on. When that prana is energy arrived there, if it is discharged, is not properly there, then it won't reach and there will be no effect in the effectors. That's what is correct. Read again.
Stimulation of the receptor leading to neuron 1
This one.
may not be strong enough to cause a discharge of neuron 3.
That is because this intermediate, the interneuron is not having enough, from here it's not transmitted sufficient impulse to this, so this it cannot transmit to the efferent, so there will be no reaction on the muscles. Read it again.
Stimulation of the receptor leading to neuron 1 may not be strong enough to cause a discharge of neuron 3. Simultaneous stimulation of the receptors leading to neurons 10
Now comes there are another receptor here, it's on neuron 10, let us say, and so there is an impulse is coming which is not very powerful. It just reached here, but it's not sufficient to send another impulse to the efferent. Then simultaneously another milder impulse coming from the neuron 10 receptor came into the interneuron, that is 11, and then it transferred to the, so both are discharging there to this particular effector. So now you see that will give you a reaction in the effector. That's what the next one, read it. So 2 different sections also can bring you a type of reflex actions. Yes.
Simultaneous stimulation of the receptors leading to neurons 10,
10
and 1
and 1
can bring about summation at 3
at 3. That means you have enough summation. Yes.
of the effects caused by impulses from neurons 11 and 2.
11, that means the interneuron 11 and interneuron 2. It's coming from 10 to interneuron 11 and coming from 1 to interneuron 2, and that together, that amount, that energy coming from these two is sufficient then to create a contraction on the
F3.
Yeah.
This is an example of spatial summation.
Read that.
Right, I'll read that whole lot again, shall I? Simultaneous stimulation of the receptors leading to neurons 10 and 1 can bring about summation at 3 of the effects caused by impulses from neurons 11 and 2, and 3 can thus be activated. This is an example of spatial summation.
T
That's right.
I A L, not that. S P A T I A. Yeah.
That's the voluntary actions.
Not finish that. You continue. Continue. So finish that. It's some of it.
Well, I finished up down here.
So go down. So go down.
Up to here. Well, that's sort of
But where did we finish?
types of reflexes.
Types of reflexes.
All reflex acts are unconscious responses to stimuli.
Okay, this is, first you have to understand reflexes. When a doctor is testing you with a hammer, what is testing? Your reflexes are in, that means there is nothing wrong in the spinal cord, the impulse are, so by testing one reflex like the knee, what is the what is tapping is patellar. So there is skin and a nerve that gets a kind of stimulation by tapping. So if the reflexes are good, what happens? It comes up. Why? Because the same impulse came, that's called afferent. From that afferent impulse came into the spinal cord, into the gray matter, and there that impulse has been transferred to interneuron, the middle one. From there, it's been brought to the, which one? To your flexor muscles, and also to your extensor muscles, because simultaneously, because extensor muscles are not extending. So what happens? You automatically, so it is not your voluntary, done through volunteer, to your thinking or to any other process involved with the direct control. That's called reflex action. So there are different types of reflex action. That's what we learned, the simple reflex action. Now we are going to learn the various names and various types of reflexes involved.
Typical examples of reflexes are the knee jerk, flexion reflex,
Knee jerk.
and the crossed extension reflex, when one leg is crossed over the other and the patellar tendon of the upper leg is struck, and that leg jerks upwards. This knee jerk results from the stimulation by stretching of receptors in the muscle that extends the lower leg. The flexion reflex is the reflex resulting...
Flexion and? Read again.
The flexion reflex is the reflex resulting from painful stimulation of the skin.
By hitting.
For instance, your response to stepping on a tack would be the flexing of your leg and withdrawal from the painful stimulus. A usual companion reflex to this is the crossed extension reflex. Painful stimulation of one foot results in flexion of the same leg, and along with that response, extension of the other leg.
Other leg also.
This is an obvious aid to keeping one's balance under these circumstances.
What will happen? Suppose you stepped on a nail. So what will happen? Automatically, if the other leg also just collapses, because you are supposed to put this foot down, and this foot doesn't want to because they stepped on, and this foot will not take the action immediately, what will happen? If you collapse, you say. So as soon as you See how wonderful the mechanism is. The moment you got some reflex action, the spine sends the word, okay, come on, move out. There is a snake. Before you can think of that, also message gone to the opposite, to do the reverse action. Come on now. Come on, tighten your, get ready, because you have to take the weight of the, that's called simultaneous action of the opposite. See how intelligently it's all paired.